Okay, so here we go. I'm going to switch to my computer. So if you go to the website, our class website, and again, I'll correct this. This will be homework 20. You can see our first cardboard 1 problem. So let's look at that quickly. You can see here, here's the beam. It has a 2-foot span. As I mentioned before in class, we're going to also assume at least 2 inches on each side for the support. So when you build your structure, it will probably be about 2 feet 4 inches, but we're not really going to model that extra part unless you'd like to. So we're just going to consider our model magically existing over these 2 feet, and we won't worry about these areas here where you might have some local failure. Also, to get started, we're going to assume that the cross-section is constant. In this case, I'm saying it's the maximum 4 inches tall, and I built layered sheets of cardboard glued together up to about 1/2 inch thick. It's a very, very simple model, really kind of almost extremely tall for its width, but let's just say 1/2 by 4. Now, our model will not consider any kind of 3-dimensional torsion or buckling, so keep that in mind also. But just a place to get started to build the model and get some results and go through the whole process. Also notice here that we have a value for E for cardboard of 58,000. And also I've done some testing and found the unit weight to be about 5 thousandths of a pound per cubic inch. So we'll use those as a model.
Bless you.
So go ahead and I'll put that away right. Oh, before we get started, don't forget too about the loading. Remember, the loading is going to be distributed over the middle 6 inches, and displacement will occur at the center. SAP gives displacements only at the nodes, so we will have a node point or a connection at the center of our structure, and it'll be a fixed connection. So with that kind of basic background, let me put that down, and I'll find the student version of SAP and start that up. I'll go ahead and make it as big on the screen as I can get. So let's go ahead and set our units down here in the lower right-hand corner. I think it's appropriate for this to be in pounds and inches. And let's go build our model. So just to make it quick, we'll build our model from a template. And the template that we'll use will just be a simple beam template. So I'll click that button. Now, we'll have 2 spans. Now remember, the spans, we really have one main span, but we want a node in the middle of our beam. So that considers a modeling span. So we'll have 2 spans. Each span will only be 1 foot. So in that case, that'll be 12 inches. And we won't worry about restraints or grid lines right now. So if I say OK, you get as you can see, you get a very sophisticated model. Looks like that. So this will be our left support, this will be our right support, and the node in the middle is where we'll be measuring our displacement, which we'll use in our formula to calculate the sum of normalized weight and displacement. So any questions? So I'll come over here on the right, excuse me, the left, and with our fast restraint button, I'll go ahead and make that a pin.
Mine already has restraints.
What's that?
Mine has 3 restraints already.
That's okay. You forgot to unclick the restraints. You can just remove them. Probably just remove the one in the middle. And then the one on the right-hand side, let's make that a roller. So we'll have a determinant problem. Okay, so we have the geometry down, and we have the support conditions. Now, one thing we want to do on this problem is we not only want to estimate the displacement of the beam, especially at this node, we also want to get an estimate of the weight. So I'm going to have 2 load conditions. So let's go ahead and define that while we're thinking about it. So under define, go to static load cases, and load 1 will be fine. I can call it load 1. That's going to be the actual load, and I'm going to make another one that I'm just going to call weight. And add that. So I'll have a weight and a load 1. So say OK. Now let's go ahead and establish our material properties. So define materials. Let's add a new material and call it cardboard. I don't know if it'll let me, no it won't. So I'll just have to call it card B. There's a limit on how long it can be. Now the weight per unit volume we've given before is 0.005 pounds per cubic inch. And the modular elasticity is 58,000. We don't care about mass, we're not doing a dynamic problem, and we're not too concerned about any of these others. And we're not going to do any design, so it doesn't matter about this material. So it's just these two that are important, the weight and the modular elasticity. And we're calling it card B. Okay. Now this particular model has a constant cross section. So when we define our frame section, frame sec 1 will be fine. Let's modify that. We are doing a rectangular section. It is made from our card B material. And what's the dimensions? Well, the depth is going to be 4 inches, and the width is going to be ½ inch. So you can see you get a little diagram to scale what it looks like. And you can see that's not going to be probably a very good actual model. It's not even going to want to stand up under its own strength. So this will be just for computational purposes, not really for actual construction purposes. For this to stand up, you might even have to put some kind of bottom plate on it just to make sure it will sit on the supports and remain vertical. Obviously, if you tried to just sit this section down on top of the supports, it would just fall over. So it needs to be stable.
I'm sorry for making you go back.
That's okay.
What was the very first thing we did before we defined the materials? I was redoing it.
I think we defined our static load cases.
Yes, that's what we did. And then we went to...
So you have a load 1 by default. We added one we just called weight. So just type in weight under load and say add.
Okay. Thank you.
Sure. Okay, so what's next? I'm going to remove the XY system. Okay, so let's click on our 2 elements, and we will assign our frame section, which is what's the cross section, what's the material, and that's our frame sec 1. We'll just say OK. There's kind of a neat feature. If you go up here and click on the Set Elements button, there's a thing called Show Extrusion, and it will show you kind of in 3D to scale what your structure looks like. That's not quite to scale. This is 4 inches deep, and this is 24 inches long. But that gives you an idea of what it looks like.
Where was
that
that again?
That was under this little button here. It looks like an X. It's called Set Elements. And you click Show Extrusion. It basically shows you your elements. This would be really nice in making sure that your sections are oriented the way you want. If you do an I section, if you do a T section or some other kind of section, you can make sure it's oriented the right way. Right now, that's oriented the way we like, so it's okay. And I'll turn that off now because I don't want to see that anymore. Okay, so what have we not done? We don't have to put any loads on it yet. So what are the loads? Remember, they're 150 pounds distributed over the middle 6 inches. So that is a uniform load of 150 divided by 6, which is what? Someone got a calculator. 150 divided by 6 is
25.
25? Huh?
25.
20? It sure is.
Yeah.
That's convenient. So 25 pounds per inch is the intensity of the load. Now, we're going to have to distribute that, the last 3 inches of this element and the first 3 inches of this element. And there's a way to do that. So let's first pick the first element, and go under assign frame static load trapezoidal. And you'll get what looks like a menu you've seen before, but it has a difference. It says trapezoidal loads. And it gives you 4 points to create any kind of trapezoidal loading. Now, I can't draw this on the screen, so you just have to listen to me talk about it. So what I have over this 12-inch element is this is what I really want to see. I want to see over the last 3 inches a uniform load of 25 pounds per inch, and that's over the last 3 inches. So I can do that by describing 1, 2, 3, 4 points. And it'll basically connect those points with straight lines to form the load curve. So the first point in that sequence would start at 0 and have a load of 0. The second point would come over at 9 inches and be 0. The third point would be at 9 inches, but at negative 25 pounds per inch. And it would stay that way at 12 inches. So this is the way I would enter that into this form. So 0, 0. Oh, by the way, too, we want to do what's called absolute difference. Distance. So then 9 inches, 0. 9 inches, negative 25. Oh, I'm wrong. These forces are gravity, so there is no negative. Gravity is down, so it would be just 25. And then 12 inches, 25. When you say OK, you can see the last 3 inches I get my distributed load.
Oh my God.
Huh?
Everything I'm doing is going backwards from what you're doing. I don't know why.
We'll try it again. Let's pick the second element. And now we want the first 3 inches. So again, we'll say assign static load trapezoidal. So now at 0, we want 25. 3 inches later, we still want it to be 25. But then at 3 inches, we want it to drop to 0. And then at 12 inches, we want it to be 0. And you say, OK, and it completes the other part. So now I have, as you can see, 25 pounds per inch distributed over the center 6 inches of the structure. And that's in load case. By default, it does the first load case, which is load 1. We're not going to do anything for the weight load case because all the loads, unless you say so, consider self-weight. So our weight load case only has self-weight. So later, when we look at the reactions to just the weight load case, that will be actually the weight of the structure. So actually, we're ready to go. So we have everything we need. So we just go to analyze, and make sure we do plane frame. Say OK. And we're ready to go. So let's run the model. Let's see, I'll give this this is going to be I'll call it cardboard beam 1 spring 14, and it's done, and there's the displacement. I'll go ahead and click on the wire view so you can just see where it was, and you can see the animation. It looks like it's behaving like you would expect. Now if you click on that point and then right click, it'll give you the displacement. So right now my displacement is negative 0.2926 inches. So I'll record that, 0.2926. So displacement at the midpoint is 0.2926. That's close enough. Now what else do we need to get? Well, what's the weight of the structure? Well, let's go over here under F for forces, and let's get the cancel. Under J for joints, we want the reactions, but not the load case 1, we want it to the weight load case. And I say OK. Now you can see my reactions are 0.12 and 0.12. That's 0.12 pounds, and I have 2 of them. So now my weight is equal to 0.24 pounds. That's pretty low. So now if I compute this, the sum of my normalized weight and displacement is the bridge weight, 0.24 pounds, plus, what's the penalty per inch? 5 pounds? Let me quickly look at the project information. It's, 5 pounds per inch. So I would then add 5 pounds times 0.2926. And I think if you calculate that, you will see it's pretty small. It's way less than 15. So technically, this would be a valid structure.
It would work.
But it really won't work. Simply because of stability. But some minor changes to it, and it would work. Some way to make it not fall over, basically. And you can figure that out. And obviously, if it's that successful, you might be able to minimize it some. In this particular case, there's about, what is that? That's about a third. So you're looking at about 2 pound penalty for displacement. If you cut your displacement in half, which would save you about a pound, and you don't raise the weight more than a pound, there would be a better solution. So that's the idea of minimizing attempting to minimize the sum of the normalized weight and displacement. So that's how we would handle that problem. Okay? So let me put that one down for a second, and let's go back to our website and look at the second homework problem. In this case, you can see there's a tapered section. Now, when I envisioned this problem, I wasn't quite sure how the weight and displacements would come out. So I just really guessed at this 4 by 1.5 inch section that we just did continuous. It seems to be working pretty fine, pretty good. But you may find that you don't want a continuous cross section. You want a non-prismatic cross section. So what I want to show you in this one, even though this is extreme, is I want to show you how to model a structure that looks like this, where at one end, it starts off with our 1/2 inch by 4, tapers increasingly down to the center of the beam, which is 9 by 1/2 inch, and then back up. So SAP will allow you to have what's called these non-prismatic sections. Now we've already got this section 4 by 1/2 in. I need to add this section 9 by 1/2. So what I will do is I'll go back to SAP, and I will save this problem as the second beam problem. And I'll make some changes. So the first thing I want to do is add that new section. So I'll define a new frame section. I think I'm going to rename this frame sec, and I think I'll just, oh, it's locked. Hang on a second. I forgot. Whenever you do this, it locks it. You have to unlock it before you can make any changes. So let's define our frame section. Instead of calling this fsec1, because I can't keep track of it, I'll just call it 4, which means it's 4 inches deep. Okay? And then I'm going to add another section. Now this kind, you can see there's a pull-down menu with all different kinds of sections. Right now we're doing rectangular. And I'll call this one 9. It's made of cardboard. Make sure you change that. You don't want to do a one weight of steel. In this case, it's going to have a depth of 9 and a cross section of 0.5. So again, you can see it's very extreme. and I'll say OK. So now I have two sections, a 4 and a 9. When you have multiple sections like this, a new option appears in your pull-down menu. At the very, very bottom, there's something called Add Non-Prismatic. So we'll click on that.
Hey, Dr. Kim, what was the depth and width for the last one?
9 inches. Now what non-prismatic lets you do is it lets you start at a certain cross-section and end at a different cross-section, and it will fit in between those two automatically. So we'll have our first section that I'll call it 4 to 9. So I'm going to go from a 4-inch depth to a 9-inch depth. That'll model the left side structure. So I'll start at section 4. My end section will be 9, and I want that transition to occur over the whole length, so I'll put 1 there. And I just say add. So now over this section, I'm going to start at a 4-inch depth and go to a 9-inch depth, and you can see that it'll be parabolic in the moment of inertia, and it's going to be absolute. I need to change it to absolute type. I messed up. So let's do this. Let's delete and put it back in correctly. So 4 to 9, 1, length, absolute. No, variable. I had it right. Sorry. Ignore that. I can't erase this because I'm a horrible video editor. So just 4 to 9, length of 1, add. Then say OK. So now you have a new section of 4 to 9. So what do we need?
9 to 4.
A 9 to 4. That's a good job to have, 9 to 4.
Mm-hmm.
So we'll start at 9, go to 4, length of 1. And we'll call that, just so I remember, 9 to 4. Oh, what did I do?
It's going to go in, you got to add it.
Oh, I forgot to add, thank you. So now, there's the two sections I'm interested in. From 4 inches to 9 inches, and from 9 inches to 4 inches. So I'll say OK. So now I'll pick the left side, and I'll say assign frame section, and that side's going to go 4 to 9. And then the right side, assign frame section 9 to 4. Now you can see it doesn't look like anything changes, but this is where that extrusion technique comes in handy. So if you go back up to elements and say extrude, you'll now see it. Okay, now hang on a second. Now, what happens is that SAP assumes the modeling diameter or dimension passes through the center line of the structure. So it looks like your structure has been turned into a mountain, but it hasn't. It maps the center line as a straight line when we know in our problem it is not. And that's okay for us. It's not that important in the model. There are ways to shift this around to make it look more like it would look in reality, but it won't make any difference in the results for us. So this is okay. Again, if you were looking at a T section or an I section, you would make sure that your flange was on the top or the bottom. You'd know it's oriented the way you'd like. So that can also be a little disturbing too, so I'll turn that off. So now we're ready to run this model. Now, what do you think is going to happen? Well, we really improved the moment of inertia out here in the middle, so I'd expect our displacements to get much smaller, and simultaneously I'd expect our weight to get much larger. So let's see if that happens. So go ahead and run it. Done. Let's see what the displacement is. It's a lot smaller. It's 0.05. Last time it was 0.29, so it went down by a factor of 5. Okay? And 0.05 times 5 pounds is basically a quarter of a pound. Right? So very little additional penalty for that. Now let's see what the weight would be by looking at the joints and the reactions. Make sure we do the weight And you can see now it's 0.19, 0.19. So that's 0.38 of a pound. So this is a much improved model from the previous one. We had barely 25% increase in weight, but a 500% decrease in displacement. So technically this would be a better structure. So I'm confident that you can build a structure and be under the 15 sum of normalized weight displacement. It seems like it's a very achievable goal.
Wait, so that one's like 1, right? 1 something, right?
Something. It'd be more. It'd be a little bit more than 1.
1 point.
Yeah, close to 2 pounds.
And that's the number that has to be less than 15?
Yeah. So it shouldn't be a problem. Since this is a new project and I just got started, I just took a shot at what an acceptable value was. So there you go. So any questions about that? So if you go back and look at this, what I'm going to ask you to do, let's go back and look at the first beam problem real quick. So you can see what I'm asking you to do in part 1. Obviously print out the assignment page. You need to draw the shear force and bending moment diagram for the structure. Print your graphics from SAP to show me the geometry and make sure your frame numbers are labeled. And then a table of your reaction forces and displacements, and then go ahead and predict that number. And part 2 is take this and improve it. So this is where you can get a chance to start maybe doing some of your design ideas. Part 2, concrete beam 2, cardboard beam 2, is the same idea as before, except we're doing this non-prismatic. So you might want to even incorporate some of these non-prismatic ideas in your solution for part 2 of the first beam problem. I probably should have put part 2 on this one, not the first one, but it all works out the same. So you should end with 3. You'll do the 2 that I want you to do, that I know what the answers are, and then something that you want to do, hopefully that improves on both of those.
So just do it 3 times.
Well, 2 times, yes.
Yes.
I guess effectively, yeah. Just do it 3 times. That is an answer to the
Well, right.
problem. You may want to coordinate with your group mate, and that you can already start building this. Because what I want to see when we're all done is graphs of how you are adjusting these dimensions. Even if you went with this shape, is 4 inches the best height to start with? I don't know. Is 9 inches the best depth? I don't know. Your values here can probably go from about 1 to 4. Here in the middle, they can go from whatever that number is all the way almost to the bottom. Now remember, your abutments are 6 inches from the bottom being the river. So you can't go 6 inches below, but 5 inches would be reasonable. So 5 inches plus whatever you do here and in. So that's quite a few combinations to check to see which one is the best. So it's pretty easy to put this calculation in a spreadsheet, and all you do is just dump in the weight and dump in the displacement. It tells you, make a plot, lowest value wins. That would look really nice in your report if you've run through really almost all the possible combinations of a particular cross-section and attempted to minimize the weight and displacement formula. Okay? So I'll go ahead and stop the video now, and that'll be that. It'll work.
Hey, wouldn't that suck?
What did it do? I have to go over here and do it.